instead of all the way in the back like some people do, because a lot of what you're going to see in this presentation is based off of other people's work. So I'm going to give credit to Kawan, who is the author of Linux Kernel Programming and is my reference for doing Linux kernel stuff and just learning. And also the Accelerator, who wrote a wonderful series called writing LKM, Loadable Kernel Module Rootkits on Linux. And really, truly, that's how I got my start as of late. I've done it in the past, but a lot of things have changed. But I felt like his approach, the way he laid out the information, made it pretty easy. So the objectives for this talk, hopefully like demystify Linux loadable kernel module rootkits, right? This isn't like something that is super 1337. It can be, but it's very accessible.
Malcolm, sorry, just can you zoom in a little, just so the folk can't see much?
Oh, I have a massive screen, so yeah. Okay, how was that?
Much better. That's perfect. Awesome. Thank you.
Okay, thank you. At any point, you can't see anything. I have a 55-inch monitor, so I could see from my backyard. All right, so like the objectives for this talk is to demystify Linux LKM rootkits. Just to show people, if you're getting started in this space, this is not something that is super hard, and anyone really can do it. They could get very complicated. Yes, that is true. I mean, you do some crazy attacks, but it's accessible to more people than you think. Also, want to kind of give you a bit of a heads up, why attackers will opt for LKM rootkits once you get to see what you can do. General workflow for writing an LKM. How to do hooking with stuff that comes with the Linux kernel, the infrastructure for really debugging and profiling the kernel is what we are going to be using to do our hooks. And also dealing with this thing called indirect branch tracking, which threw me for a loop and is still throwing me for a loop, but you'll see coming towards the end. So the first thing we want to look at, or the first thing we want to understand, is user space versus kernel space, right? The kernel has its own sets of privileges and memory, and that is separated from the space where you would execute regular applications, such as your web browser, where you run your shell, where you execute programs in your shell. And the reason for this is to provide security and system integrity. For instance, you wouldn't want to be able to do to execute special instructions like mess around with your interrupt descriptor table or your global descriptor table, because that really could destabilize the entire system to the point where a user-based application wouldn't just crash, it would take the kernel along with it. So the CPU really allots for 4 rings of privileges, 0 to 3. But on Linux, we use ring 0 and ring 3. Ring 0 being the space where, or the privilege ring that the kernel will operate in, and ring 3 is where user space applications will operate in. Certain instructions, like I just mentioned, load interrupt descriptor table, read MSR, write MSR, etc., can only be executed from ring 0, and that's enforced by the CPU. Let's see, sorry about the long let me move on. So Ring0 is, again, we refer to that as kernel space, and ring 3 user space. So the kernel, this is starting to add towards like why it might be attractive for an attacker, right? So the kernel is responsible for a lot of important functionality. It's going to create a large portion of your network stack. I actually took the time to like really think about which layers of the OSI model that the kernel is directly responsible for, and quickly realized pretty much layer 2 to 4, and the other layers above it, it can influence in some way or the other, right? But directly, you're going to see code in the kernel for layer 2 to 4. You won't see HTTP handling in kernel source, right? Which I believe is, yeah, I don't know. Not sure which friggin' layer it is, but not a networking guy. All right, so besides that, it does things like handling peripheral devices, so like your hard drives, your solid state drives, character devices, that would be keyboards, mice, serials, your network device card, etc. And of course, if it's handling those devices, you can do things like be the intermediary between reads and writes from solid state drives, right? So maybe hide files, right? Capture keystrokes, um, mess with network traffic, right? Um, so there's like two ways on Linux, at least, that you can communicate with the kernel directly as a user, right? The most conventional way is through system calls, right? And I say that's a fundamental vector for communication with the kernel because these secondary options, which is through pseudo file systems like, procfs and device files, etc., like, dev random, dev random. Um, those really require you to make a system call on those files to then communicate with the kernel. All right. I think I was supposed to have something here, but we'll delete that. And the general idea I'm trying to pull out here is that these system calls is kind of a key area a lot of loadable kernel modules will hook in order to perform their business, right? So this is about, at this point, we're doing a Linux kernel follows a monolithic design. What this essentially means, if you look at this diagram, and it's quite simple when you think about it. Everything the kernel needs to run is in one ring 0. So the networking, the device drivers, the memory management unit, um, all in ring 0. And then there's ring 3, which is all your user-based applications. This is what's known as a monolithic design. The rings 1 and 2, again, they're there, but Linux doesn't use them. And I actually did a tad bit of research, and it's not very popular for modern day operating systems to not follow this monolithic design. Right? I believe Windows does the same thing. All right. Anatomy of a loadable kernel module. This is the source code for just essentially a simple hello world, LKM. It's written in C, and there's a couple of things that you'd want to pay attention to here. Is just there's this module init macro and module exit macro, where we define where we want execution to start, and upon removal of the module, what function we want to execute. If you are familiar with object-oriented programming, it's essentially, not in a technical sense, but conceptually similar, right? You have a constructor routine and destructor routine upon instantiation and deletion of an object that would execute. So the kernel allows for a similar function with kernel modules. We have these annotations here that allow us to define these entry and exit points, if you will. To get a little bit more into the weeds, the include directives you see up here aren't coming from /user/include, like where you'd call stuff for making user space application. Instead, you would be using them from the limited kernel source that you would use to compile kernel modules. And the way you get this limited source is typically you would, whether you were running Ubuntu or maybe Arch Linux like I do, you would essentially tell your package manager to install the Linux headers and whatever kernel version you're running. And that will include the headers. We would then compile the kernel module using a makefile that we really use to reference a much larger and much more involved series of makefiles and configurations. That's part of what's known as kbuild. It's the kernel's build system, right? So we have here the makefile that I use to compile my module, which I've called it Venom. I know, corny name, but whatever. I was looking for something edgy. And this makefile does make taxi, and then there's an argument here that essentially points to the build directory in the limited kernel source tree that contains all the header files, the configuration files, etc., for my particular version of the kernel. If you compiled your kernel yourself, like you're running Gentoo or something, they should already be there, and you could just reference that. I use Arch, so someone build my kernel for me, and then I could request the headers. And when you say make in your directory where the kernel module is at, you're basically saying, okay, change to this directory. There's going to be another makefile there, the kernel's makefile, and I have it highlighted down here. Invoke that. Oh, and by the way, what I'm trying to do is I'm trying to build some modules, and the kernel will then say, okay, let's make those modules, and it will go back towards my directory and begin to build those modules. Now, I have here describing the actual arguments and whatnot, but I don't think we need to get too detailed. But the gist of it is this is important that we use the kernel's build system, kbuild, for building our kernel module, because we want a nice pairing between the kernel module and the kernel itself. And when I say nice pairing, I mean we want to be compliant or congruent, right? Whatever parameters were used to compile the kernel, we want our module to be built with those parameters, because we don't want to try to load the kernel module and come to find out, well, our module is using some features or lacks some kind of features that the regular kernel doesn't have. So they don't join together, and we get a crash, right? There's an application binary interface that the kernel enforces or expects modules to follow in order for things to mend well, right? For it to be linked into the image of the kernel and doesn't cause a system crash. So that's the real reason why we would use kbuild, right? Linux kernel hooking. So hooking in the Linux kernel for a rootkit, that's life, right? It allows the rootkit to do useful things from attacker perspective. For example, if you want to hide from system administrators, you can do things like, tell this kernel module, hey, if you see a process by this name, make sure it can't be seen from user LAN. Or if you want to hide a specific directory because for whatever reason you need to stash stuff there so your implant can persist, or I don't know, maybe you're doing some type of processing on files or whatnot, and you don't want anyone to be any wiser, you can hook certain system calls to be able to blind user space applications from this reality, because user space communicates with kernel space typically through system calls, right? So if you could play man in the middle, you get to set the scenery that these user space applications can see. And we want to do these hooks using the kernel's infrastructure. And by that, I mean, the Linux kernel has like a lot of cool features. Two of them for this talk that you should be concerned about. Let's call like ftrace and kprobes. Ftrace stands for like a function tracer. It's really a built-in tracing framework that developers or even sysadmins really can use for debugging the kernel or getting performance information, just trying to figure out what's going in the kernel, what's happening in the kernel while it's running. And the APIs for ftrace are exposed to user LAN applications through what's called a tracefs. Similar to procfs in the sense that it's a pseudo file systems, and writing and reading from it allows you to do things or tell the kernel to do certain things on your behalf. And there's also APIs available for LKMs. So you can still use this tracing framework from within a kernel module. You don't have to do it from user LAN, which is important for us because we're going to be using it to actually hook things. And the next feature would be kprobes or kernel probe. And the gist of that is it essentially allows us to put a breakpoint, an AIM3 instruction, right? Software breakpoint on kernel code. And we can register what's called handlers, which are really just function pointers to be called towards routines that we can define before before the AIM3 instruction is encountered or after. And this part is critical to one of the objectives in writing a modern day Linux kernel rootkit. You could think of it like this. Yeah, we have a LKM. We need to dynamically figure out what's the address of the functions of interest, right? Modern day kernels, Linux kernels are going to have KLCLR, which means the address of functions changes at every boot. So we need to figure out live what's the address of, say, something like makedir. And there is a function that the kernel used to export called call sims lookup name. And what it does is you give it a function name or a symbol name, and it will return the actual address, right? this was really nice back in kernel 5.7 and prior, because it allowed us to figure out, hey, where's this syscall that I want to do a hook on? But they took it out. It's no longer available freely or through the paths that the designers want you to take. The reason for this, or like a myriad of things, one of them was they wanted to enforce licensing. So if you have a kernel module that has a GPL license, GNU Public License, I believe that stands for, you can access certain export functionality from the kernel. Whereas if you didn't have GPL, you couldn't, right? And what people were doing is like, oh, well, I'm not GPL, but I want to access these functionality. They would just use KAllSims to essentially do, I don't know, maybe for Windows people, essentially do like a load library or a DL open where you could resolve a symbol directly to an address, right? So you're not rely on that being linked in, and that would bypass it. That would bypass that. The other thing is it enforces the kernel's application binary interface, which basically is a sort of an agreement to say this is how we're going to invoke functions, this is how we're going to return things. It's a convention used so that everyone's on the same page, so that we don't have crashes, right? And when out of tree module, so a kernel module that you and I could write is out of tree. It's not part of the kernel source. When a kernel module can do things that's it can invoke functions that isn't exported, this is a violation to the ABI. So that's another reason. The third reason, which really isn't listed here, I think I was supposed to list it, but I didn't. I forgot. They wanted to be a pain in the ass to people that like to write LKM rootkits, right? Make it harder, not make it so trivial. And that aided in making, I guess, I mean, not really, but really, not really. That was supposed to make it harder to write loadable kernel module rootkits. All right, but going back to kprobes, we can use kprobes to access this function, right? Sorry, fixing that. The KAllSims lookup name function, and I'm going to show you how that's done. This is obviously a struct kprobe. I have it here because it's just important. What we're going to do here is we're going to set this field to the symbol that we want. We're not going to use this to actually do the hooking. We're just going to use it to resolve this particular symbol. So then we can then write a wrapper to resolve any symbol or any function, find out its address so we can instrument it, so we can hook it. So we only fill out this field, and I have the function here from my little POC that I went ahead and coded up, and it's called get KAllSims lookup name, right? Just as I said, I only fill out this field, the dot symbol name, and then I register a kprobe. Right here, I pass the struct in, and then I get this field, the address field, populated for me, right? Which is interesting. And this just so happens to be the address of this symbol that I put here. And it's simple, but like when I first started like doing this stuff, I'm like, don't the maintainers know about this? You know, it seemed a little bit like magic, but I guess I don't know. I was a little bit more curious, so I looked at register kprobe in the Linux source, right? And you can see it's passing the kprobe struct that we just passed to this function here, underscore kprobe underscore ADR. And above it says canalicalizes probe address from symbol, right? And then this returns an ADR. There's a test to make sure it's valid. It's a valid address. I actually went one step deeper and looked at this. What's happening here is they're essentially resolving, obviously, but I just wanted to show you where this is happening in code. They're resolving the symbol to an address and then plugging it in for us, and execution continues, right? So that's essentially how that works. It's no voodoo that's happening in the background. You can check this out a little bit deeper if you'd like. I know I did. So the next technology we want to look at is ftrace. Ftrace is the bread and butter for implementing the hooking mechanisms. It's very stable, supported, of course, by the kernel. Before the ftrace was introduced, people used to do stuff with like kprobes and literally modifying the interrupt descriptor table to intercept system calls, and it was messy and probably not as stable. Definitely shouldn't be doing it now. There's a lot more mitigations in place. Things just, I mean, I've tried some old stuff and didn't work. Later found out that, well, there's protection for that. So, best to use this infrastructure. So going back to ftrace, the struct above ftrace_ops, that's a function, sorry, a struct that we'll be passing in to several ftrace API calls. And it's pretty self-explanatory. The first field is a function pointer to your callback. You can set some flags, and which are important for describing to the APIs how your callback, what you'd like from your callback, what your callback intends to do, etc. This field, no use for it. I personally haven't touched it. So the first call that you would see, and I'm going to show you down in the source code down here, is to ftrace set filter IPs. And what this essentially does is it says, I'm going to give you an IP address for a function. I only want tracing on that particular function, because ftrace is capable of tracing a whole bunch of functions. All right. So we need to like say exactly what is it we want to trace. We don't call this function register_ftrace_function to enable the tracing, and then we want to tear everything down when we're done in with onRegister ftrace functions. All right. So we disable tracing, and this is the source code. I actually took this out because I didn't want to give a memory address of my running kernel. But this is a function that I wrote, modified version of the accelerator ftrace helper. This, you'll see something similar in his. And I wrote it. I had to kind of like reinvent the wheel a little bit because I just wanted to understand it a little bit better. And I felt like if I had to write it, look at the documentation, make mistakes, have shit crash, I'd better be able to understand it. And the idea behind it is I could give myself an array of targets that I'd like to hook right here. Specify a count because, it's an array. We don't really know where it ends. It's a dynamic one. And I will go ahead and first get the function name. I'll resolve that to an address with my KLSIMS lookup name, right? Then, of course, I call get KLSIMS lookup name up here, but like this is where I'm going to resolve the hooks. I get the address. And then I start to fill out my my FOPS, ftrace operations struct with the arguments. This is like some recursion protection. Let it know that we're going to modify the instruction pointer, and also we want the registers that were used to that were supposed to be passed, or the arguments in the register are supposed to be passed to the thing that we're hooking. We set the filter, we register it, and then we're on to the next one. Oh yeah, there's this original func that's for calling the original, for storing the address of the original function so that we can call it later on. And this is supposed to run in a loop. And I'll show you later on where you can just create macros to then define the functions that you want to hook. And this is essentially what my callback looks like. I wrote this, it's been a while, some time back. I was looking at like, holy crap, what the hell is happening here? But it looks a lot different than the accelerator's implementation for his ftrace callback. I believe it's because I figured out a couple of things so I didn't really need all those macros. Well, let me clear this up. So this ftrace callback, there's a no trace qualifier here on this particular function. And the reason for that, if I recall correctly, is that we wanted to prevent tracing ourselves, right? Like that's a way of telling the tracing infrastructure, like, hey, this is off limits. And our arguments in this particular function, ftrace is going to expect us to be able to handle these arguments, right? And so these must be defined in your callback. Whether or not you use everything, that's up to you. But I mean, I guess if we want to stay programmatically compliant or to the ABI, but essentially, I define these because this is the prototype that they are expecting to have. I get the registers state for the thing that I'm hooking, where I can then modify the instruction pointer and have it point to the function that I want it to execute instead of the original function. There's a check up here called within module. And this is, I believe, this is a recursion protection, right? I wrote this a while back, so bear with me. This is prevent recursion. So you can have situations where your target function is being instrumented, being traced, and then how do you know, like, you don't have a tracing event within a tracing event type of thing? So Linux has this macro within module that allow me to eliminate a few lines of code from the accelerator's implementation of it. All right. And then there's essentially on registering the hooks. This isn't that interesting, but you call this, right? You don't want to hook everything all the time, or at least you want to clean up after you offload the module, right? Okay, so I have all of that stuff defined in rkit_helper, and I made one hook for myself, which was I want to hook make dir, and let's see here. Okay, I went ahead, compiled this, and loaded it. And this is the debug message, DMESG, that utility to see, kernel debug messages, info, alerts, etc. So you see Venom in. I successfully hooked sys make dir. That's how it's defined in the kernel, make dir system call, as far as the symbol name goes. And then I did a test. So I make dir tests underscore Venom, and it successfully hooked. I then offloaded the module, so that's where you see all this stuff pops out. Not particularly the most entertaining offensive thing. I do have code for that. It's just not complete, and I just don't feel comfortable releasing it right now. But this is enough for just you to write your own hooks, right? I don't know, get creative, take a look at accelerated blogs. You can start to implement some of the stuff in there, right? Like your easy kill to root from unprivileged user to regular user, or mess around and hook into the network stack. But okay, on to something a little bit more interesting. So there's this technology called indirect branch tracking that set me for a loop. I was developing an LKM in my VM, and everything was working fine. I had some hooks in the network stack going well. I could turn certain features on and off with ICMP. I mean, it was great. And then I decided to move it outside the VM, and I placed it on a laptop. And lo and behold, I got a crash. Like, what is going on here? Like, I compiled it, with the Linux version kbuild on that system, and that's when I ran into indirect branch tracking. So indirect branch tracking is a hardware security feature introduced by Intel, part of CT. Not the stuff that you get when you play too much football, but control flow enforcement technology. And the basic idea is it's supposed to make ROP and JOP, return-oriented programming, jump-oriented programming, exploitation harder. And IBT is triggered when you execute indirect branch instructions. And that's basically jump, either the jump or call instructions or more, right? But if the idea is, if the location of the jump is calculated at runtime, the indirect branch tracking needs to look for an instruction. On my system, I run x64. It's NBR64. So you can even see this on Linux. I believe GCC 8 and up. If you disassemble it, you'll see the NBR64 instruction, which is really a no-op. It's just an annotation that the compiler would place there to say, okay, this is the start of a legitimate jump-in area, or area that you could call into. Seems like all the functions really have it, to be honest with you. But the IBT security feature on the CPU looks for it anytime there's an indirect jump-in event. And if it's not there, it'll raise what's called a control protection fault. And if you're doing LKMs, that results in a crash. Ultimately, a joint venture between the compiler and the CPU. I think I just kind of pretty much summed it up, right? The compiler has a purview, or not even a purview, like is a sort of the best place of knowing where or understanding the control flow to actually inject these annotations and figure out, hey, should a NBR64 instruction be here or not, right? And if it could probably do that, it would then do like, maybe relative call instructions or relative jumps where the offsets and stuff are hard coded in there and it's not dynamically done. So it's a joint venture. You can't really have this feature without the compiler helping you out. Yeah. So this was introduced in Linux kernel 5.18 and enabled by default in kernel 6.2. It creates a problem for us because when we instrument a function, what we're essentially doing is we are placing a stub of code at that instruction that's supposed to call back into our tracing infrastructure, and we'll get a location. It will dispatch to the hooks that we register, right? The problem happens when we try to then do we then we try to call back into the original function. As you could imagine, that's dynamically done. So we're going to produce instructions for an indirect jump. So either jump, register, or jump call, or call register, or uh, something dynamic, right? Not hard coded, memory or registers. Can't remember if that's an illegal instructions or not, but you get the point. I was trying to figure out what the hell was happening here. And when I did figure it out, I started to get like sort of crafty, or I thought I was being crafty. It's like, all right. Maybe I could write the NBR64 instruction code back to that location. So yeah, I would need to then tell the CPU these pages of memory left for the kernel code needed to be writable. And to do that, you have to flip the write protection bit on a control register 0. No luck. Things crash still. Later found out like there's some hardening against this. And it's not a good idea to do that because it could potentially destabilize the kernel. Then I was speaking to a friend of mine named Chernobyl from VX Underground, and he doesn't do Linux stuff, but he does pretty low level stuff. So our work overlap when it gets low enough. And he's like, "Oh, I think that might be something in model specific registers. I might have read something about that." I was like, "What?" Immediately, Godspeed. I went to the Intel manuals, and I just face palm like, "You dummy." You could essentially turn this feature off momentarily, or for however long as you find fit. So in the Intel manuals, the specific MSR register correlates to this specific hex 6A2. And the position in the manual states the second or bit position 2 in this particular MSR is responsible for enabling and disabling IBT. I went ahead and dev'd out some more code here to essentially, one, we need to see if this particular environment supports IBT. And if that's the case, we need to toggle it, right? We need to toggle that bit so we could turn it off before we go ahead and install our hooks, because we don't want a control protection fault to be invoked and crash our kernel. Sorry. And so this code is now part of my implementation of ftrace helper called rkit _helper. Yeah, seems like it come to an end there, but I just want to note this. Today I went to actually try this stuff out. I removed the IBT toggling portion of the code, executed the rootkit on the system that's supposed to have IBT enabled, and guess what? It worked anyway. This is starting to look like there might have been a kernel bug, because when I was researching this, I'm like, didn't anyone realize that IBT would interfere with ftrace? Like, how could they do this? Do I have to turn off critical protections just to be able to profile or debug the Linux kernel? And apparently someone agreed with me, but I just found out about this today. I've been kind of like sitting on top of this research, doing my own thing. Once I figured out all the hooking, I was writing other stuff. So I can later on in the future maybe do a blog post to maybe clear this up. But as of right now, what this looks like is this IBT toggling should apply to certain versions of the Linux kernel if it's not patched. Yeah. But anyway, questions? Hello? Hey, Rad.
Look in chat. Oh, okay. I can read questions out.
Oh, I'm sorry. There's a chat. I'm a boomer, guys. I'm sorry. All right. Okay, hold on. Let's see. Let me scroll up, scroll down. Sorry. Okay. Okay. SABZA. What's your kernel address? None of your business. All right. Rad, how did you get your dev environment set up? What does it look like? So the dev environment is basically, of course, the GCC toolchain, make, and the Linux kernel headers that you have to install if you're going to be using the K-build system to compile the kernel modules. Don't think I'm really missing anything else. I mean, there's specific setups I use for programming and stuff like that. I use like NeoVim, and an assortment of plugins and stuff through Lazy Plugin Manager, but I don't think that's what people really want to hear. But I guess GCC, the make utilities, and the limited kernel source tree that you can either apt-get or pacman, whatever package manager you have, you can install. It's pretty, not a whole lot, you know. And of course, it's nice if you do it on a Linux system. Okay, let's see. I think some of us feel stupid. No. This is all in your head. This stuff is a doozy. You just need some time. It's okay. I see another question. So I've been learning some kernel stuff and want to hook exceptions like be the topmost. Do you have thoughts on how do something similar to KI user exception dispatcher hook in Windows, but on Linux? Is there a good way to get set thread context the same way? I would have to think about that. I don't really know a whole lot of Windows kernel stuff outside of what I've read in books, which isn't even that isn't a whole lot. So that's something I'd have to sit down and think about to find the analog on Linux. Matthias, using ftrace is good because it works in recent kernels, and syscall table hijacking doesn't work most of the time. However, most rootkits that use ftrace are easily detected because they don't hide from tracing sysfsm, making forensic work much easier. That is true. There's another angle to this, which is, hiding your presence on the system. It will be a lot to cover all of that in one talk. And personally, I haven't really rolled up my own sleeves to really dig into that avenue. But it's a cat and mouse game, and it can get pretty technical and maybe outside the scope of this talk. I am using Arch Linux right now. No, I did not build a kernel. So Arch, the people that are compiling the kernel for me, they're just providing the limited kernel source package also with it. So yeah, you can go ahead and you don't need to build a kernel on your system. It's a nice thing to do. You learn a lot, but you don't need to do it. Is there a newer version of syscall tables in a Linux kernel or something? There's been changes on how it's invoked or implemented. What you can do with it. Can't really speak to it because I've been working pretty much with kernels 5.7 and up, and on more modern systems. Is there a specific structure you use for organizing your discoveries and working code bases? Yeah, there is. I use again NeoVim with a bunch of plugins for quickly grepping and resolving references, etc. If that's what you mean, the actual mechanics of how I'm doing that stuff. Organizing, a lot of Obsidian. And as far as understanding this stuff, just you kind of have to pick an area and drill in. Do you mind more personal questions about yourself? In DM if you want. Why don't you use QEMU to emulate kernel? It's more reliable for debugging with GDB. This is true. Why don't I, right?